So is there any news from people? Or,
I'm visiting from Edinburgh
yep.
today. I'll be around in a couple of hours. And I work with Sam Whitney over there. We're very practical programming and stuff
And your name is?
Oh, my name is I'm just visiting.
Oh, WebAssembly.
WebAssembly.
Yeah. And there's no other news whatsoever.
I don't know what causes anything to today.
Okay.
What can you
Well,
give us some examples? Yeah.
Example. Man bites dog. Yeah. Yeah. Ah,
We had about 160 people for a conference in London, which was almost for 15 years. I had to pay for the kebabs for the dinner, my own credit card, because of the university law.
what was the conference?
The conference is solid, something which you should have if you went there. Because you have this privacy website, the data.
Yeah. Oh.
Which sounds like that's a good thing. So, yeah.
I'll just get started. So this is a kind of silly little results that I've been meaning to write up for a while. And it's glad I did for this because I actually found a small mistake. So this isn't quite true, but I'll get to why it is nearly true. But basically, this talk is in three parts. What are containers? What are coherent spaces? And then how to embed the former into the latter. Okay, and I guess everyone is meant to be general knowledge in MSP what a container is, but I'll say anyway, because there might be some people who don't know. So a container is, right, so just plainly, a container is a pair SP where, let me do that differently, S is a set and P is a family of sets indexed by S. And this is meant to be a kind of it's basically as minimal as you can get and still be a dependent type, right? You've got a set of things and then a type that depends on that set of things. And there's lots of different ways of understanding this. So you could say S is shapes. And for each shape, it has a set of positions. So you kind of think the shapes might be sort of skeletons of trees, and the positions would be the nodes in the tree where I can hang things. So it'd be enumerating those nodes. Or the shape might be a natural number, which is the length of a list, and the positions would be the finite indices in that list, the set of finite indices. So P is positions. Another way of thinking about it is that S is questions, and P is answers. So S is a question like, what's the weather like? And P is the set of answers which are relevant to that question, or valid answers to that question. Related to that, intervention, P is solutions. So here you might have something like, I would like to prove some statement, and the set associated with that statement is the set of proofs of that statement. Okay, so there's lots of different readings of this kind of setup.
Well, currently, before you're from you can change the position.
Is that better?
Yeah, you can change the position.
Position, yeah.
You change your shape.
No, try. Right. Okay, and the extension of a container SP, is a functor on sets, which is defined to be, so I'm going to use these square brackets, SP. So this gives you the container idea. So the idea is that we're going to define an operation on sets where we're going to have a new set where we say there exists a shape, and for every position in that shape, we have a value of x. Right. So an example would be if the shapes were natural numbers, so that's the length of the list, and P for every natural number is the set of natural numbers less than that natural number. Okay, so we'd have, that's n, and for every n we have the set of I is less than n. And then if you work out what this means, that means, well, which one? This one. Oh yes, sorry. This is a dependent sum. So this is a pair of a shape in S and a function from P of S to X. This is bracketed like this. Summing over all the values in big S. Yeah. So yeah, you can think of it as if this had 3 elements, yeah, it would be as Sean said. Yeah, so this is a co-product over all the values of big S. Yeah. Right, and so with this example, then we'll have a typical value of this would be some number n, and then a function that takes an I in this set, so this is some I which is less than n, and gives you some value of x. So that's going to be lists, right? So this container, natural numbers and the positions are indexes less, is going to be, when we take its extension, it's the list functor on sets. Right, but now we're representing lists as a pair of a length and a function from indices to values, not the kind of inductive way of doing it. So this is why they're called containers, because they're a way of representing these kind of container-like data structures like lists and trees. And
So which one is list again?
this is list. Yep.
Sorry, I'm struggling to read the watch my smart capital lambda lambda I.
Oh, this is an n.
Oh, n.
Right. So this is a value which would be in this.
Right. So and then after lambda
Less than.
Oh, that's a less than.
Less than n. Yeah. Yeah.
Just make sure I understand. So the container definition doesn't have any content. It's just fairly.
Yeah.
But the extension of the container has content.
Yeah. So once you supply an x, that'll be a list of x's.
Got it.
But we could also have shapes are shapes of trees, and the positions would be, depending how you want to do it, there could be the nodes in the tree, that could be where the data lives, or it could be the leaves in the tree, that could be where the data lives. So it's quite a flexible definition. Yeah. Um, then next part is a container morphism. From SP to RQ. So I'm going to define, so I've got a collection of things called containers, and I'm going to define what a morphism is between them. So a morphism between them, it consists of a pair of functions that I'm going to call f and f bar, such that f is a function from shapes in one to shapes in the other. That goes forwards. So it is mapping shapes in one to shapes in another. And then f bar, what does that do? This is dependent type notation. It's going to, for every shape and every position in the shape that maps to, we get a position back again. Right, so we go forward at the top on the shapes, but we go backwards on the positions. So another way of thinking about this is if you know anything about lenses, then lenses are exactly this, but there's no dependency. So we've got the original shape, the output, and we get a new input. Yep.
Maybe a stupid question, but if this is related to lenses, but this adds the thin top, what can this do that lenses can't?
So the main thing is that containers, you can take sums of them, co-products. Lenses, you can't take a co-product. And the reason is that in the two halves of the co-product, the positions would be different. But a lens, the positions are always the same no matter what the shape is, because you don't have the dependency. Yeah, so that'll be the definition. Is like where P is constant, then that's a lens, or a so-called bimorphic lens or polymorphic lens.
What's the intuition for why that?
So if you look at this definition, this is in a negative position, right? So what we're going to do, so if we have the extension of SP and the extension of QR, then we want to map one to the other. So we have a shape, we can map that to the shape. But then this is in a negative position, so we're going to have to go backwards. We're going to have to pre-compose with that. So yeah, the point is that this is something we're given, but this is something we have to give to get an X out. So we have to map backwards.
And if you look at the questions, answers, intuition, it's a bit like a reduction.
Yeah.
Transforming questions of one and then bringing the answers back across.
Yeah. So it's extremely similar to like reductions in complexity theory. You're reducing a problem, but then given a solution to that problem, you come back to a solution to the original problem. Oh, sorry. The question there, we figured that was why is this backwards? Okay, so that's so the final point I want to make here is that every container morphism gives you what's called a natural transformation of these functions. So that's so as to say that if I have f that goes from SP to RQ, then there is an f that yeah, because the other one is well, which you can think of as that for all x is going to give me something that goes from SPX to RQX. And when I say natural, what I mean is if I had another y, it doesn't matter if I apply that and I have a function from x to y. Doesn't matter if I do that first and then go across and then end up there, or do the mapping and then do the y. So it's natural in that sense. And this gives you a functor from containers into functors themselves from set to set. So this extension goes from the category of containers with these morphisms into functors from set to set. And one reason to think this is a good definition is that this functor is full and faithful. So that means that not every functor from set to set is representable as a container, but every container morphism between, sorry, every natural transformation between container morphisms can be taken back to a container morphism. So it's on morphisms, it's an isomorphism, but not on objects. So you have like an embedding. So this category of containers identifies a nice subcategory of the functors from set to set. Gives you more than the finite tree, because you have this large amount of. Yeah, so if you restrict this to finite sets, then you get the sum of the finite tree ones. And also the reason for studying containers, apart from all of these different readings, is that they're closed under a large number of operations. So you can take the product of two containers, you can take the co-product of two containers, you can take the function space of two containers, which is a little bit surprising. There's another way of taking two containers, which is like sort of parallel composition. So I'll just explain what I mean by these things. So we can take S and P times RQ. What's this? Well, we take the product of the positions, but then for any pair, we take the co-product. So we take the product of shapes, sorry, but we take the co-product of positions. This is like I have a shape which is in both, but for any particular position in that shape, it's only going to be one of them. Then there's also co-product. This is S plus R. And now there's two versions. If we've got in left S, then that's going to be PS. If we've got in right R, that's going to be QR. Right, so now we have a choice between which shape we want. And of course, if we pick one of them, then the positions can only come from that. And these correspond exactly to doing the same thing on these functors. We can take the product of two functors, we can take the co-product of two functors pointwise. So this means that not only can we do this thing where I said, oh, you can make lists, you can build them up incrementally, these operations. And then there's some fancier things we can do. So we have a tensor product. This does what you might thought we should do for this one, which is you take the product of the positions. Like that.
What's the intention for that one? So two skeletons and two different shapes.
Yeah.
And one half of one and one half of the other.
Somehow what you've done is you've worked out a way of taking this x and dividing it into two, and half of it works on one, half of it works on the other. Yeah, as a data structure, this is quite hard to think about, but as questions and answers, what does this mean? This means I now have two questions, and you have to answer both of them.
It's like a generalized matrix with a position on each axis and something in the cell.
Yeah, yeah.
I guess in terms of data structures, I could think of this as like a copy of Q in a copy of R. Sorry, I keep on confusing division and change, but a copy of the data structure basically at every point in the other data structure, right? So you have a track and then
That,
really
that's going to be the next one.
Oh,
Yeah. Yeah, I see what you mean, but yes. Right, so this one, I ask two questions, and you only have to respond to one of them. So you get this kind of choice about which one to respond as the other person. This one, I ask one of the questions, then you have to respond to it. This one, I ask two questions, an S and an R, then you have to respond to both of them. This is a bit like in terms of kind of search, there's this and or. You have to answer all of these subgoals, or you have to do one of the subgoals. This is like the search. My task will work if I answer one of these. My task will work if I answer both. This is like different choices. And then one, which is a bit more like what you were saying. This is a composition product. What's this? Well, this says, I'll ask a question on R. Once I get a response on P, then I'll ask another question on R. And a response to that is a response to both. So this is a kind of sequential. So this is going to be ask a question here, given a response, I ask another question R. Yeah, and that's actually the extension applied to R. And then given S, and I'm going to use R, but really this means the function which returns an R. This is a pair of an S answer and Q answer. Okay. And this one actually corresponds to composition of these functors, which is quite nice. So if you've got two containers and you take their extension and then you compose them, the resulting functors, you can apply this to the two containers and take an extension and you'll get the same thing. Yeah, so we've got a category that has products and co-products. In fact, they distribute. We've got a monodal product, which is symmetric, so you can swap it over. You can just swap these pairs. And we have a non-symmetric product as well. So it matters that SP goes first, not RQ, because there's an order. Because again, this is because functor composition works. Yeah. Don't know. I'm kind of running out of time because I haven't talked about coherence spaces. Yeah. Yeah. Types. So this one's not commutative. Sorry? Yes, it does. It does, but there's no negation, so it's not a model of movement. Yeah, so the just leave it at that. It's like I think I'm pretty sure it'll be a model of right. This is no one else in the room understand this. A model of intuitionistic BV, which is a particular logic which has these connectives in it, but also has a negation. So we don't have a negation here because there's no way of like swapping. It does obey the rules. Okay. Yeah, I was just all right. So the key to that conversation was that there is a logic that has, like linear logic, with and product and a tensor product also has a non-commutative operator, which will come up later on as well. Yeah. No, because won't be. It has to be involutive. You'll get okay, everyone happy with what a container is?
And then we say that we can also do differentiation.
Yes. You can do exponentiation with respect to this one and this one. I've forgotten the definition for this one because it's weird. This one's the easier one because it's. I know I don't need it later, so I'm gonna, yeah. Yeah. There's a function space associated to this product and to this product. So you do get a model of bunch duplication as well. Yeah, yes. Just need to more questions, which we don't have time for now. Okay, so that's what a container is, and some constructions on containers. There are also things like greatest and least fixed points as well, which is nice. Okay, so what is a coherence space? A coherence space. All right, so a coherent.
One last question.
Yeah.
And maybe we should be done. We never about containers versus polynomial space.
Functors.
Polynomial functors.
Yeah.
The idea of containers was to get a nice syntax to describe this, or in the way we do it. Because I mean, we had a syntax for polynomial functors, it was just inductive definition. But then it would be difficult, I guess, to get down to this. I mean,
Okay, so maybe I should say that. So one way of looking at this is it's a bit like a polynomial, right? So if I rewrote it as the sum over s of x to the ps. Now this is kind of like a generalized polynomial, where instead of a number of degrees, I have a set, and instead of for each thing I have a number, I have a set of things that come from. So these are like generalized polynomials. You can give, yes, this was, I think the reason that the people in the Midlands, like Neil and Connor and Hank and Michael Abbott, wanted to study this was that it's a generalization of functors that you can build from plus and times and so on, which represent the kind of normal data types you use for making data types, right? But it allows infinitary positions, things like that. It's also related to what category theorists call the category poly, which is a sort of sort of all of the members of this, which can be represented as containers. So it's a subtly different definition in that it takes the fact it's a functor as primary, and it can be factored as something like this. Whereas this is, if you like, the codes for it. So it kind of affects what you mean by two things being equal, for instance. So some people call these polynomials because of this thing, but they're kind of generalized. That also means you can take the derivative of them as well, if you've got a kind of notion of -1. A coherent space. So a bit of history of coherent spaces. So coherent spaces were developed by Jean-Yves Girard as a model, as a way of giving a model of system F, which I'm not going to talk about. So system F is the type lambda calculus with for all types. And the tricky thing there is that if you want a for all type, you've got to make a type by quantifying over all types. Right? And you can't do this with sets. So you can't say a type is a set because you can't quantify over all sets to make a set, because that gives you an inconsistent set theory. So coherent spaces were designed because you can kind of approximate a coherent space by taking larger and larger ones. And that allows you to approximate this for all by taking bits. They're also the way that Girard discovered linear logic, and I'll explain why later. But so, and the other interesting thing about them is that they have many different definitions. So a coherent space is a set. So a coherent space X is a set which I'm going to call bar X of tokens, and then one of the following three things. So either a set which I'll call curly C x of subsets of x of the tokens such that it's A downward closed. So that means if I have alpha, which is contained in beta, which is in curly C of x, then alpha is in curly C of x. So if a subset is in it and it has if a set's in it and it has a subset, then that subset's in it as well. B, if you have a set of sets which is contained in here, and for all alpha and beta in A, alpha union beta is in A, then the union of A is in curly CX. This, if I have, if you like, a collection of approximations of a thing, which are compatible in the sense that anytime I take two approximations, that's taken as being set as well, then I can take the union of all of those to get the kind of thing that thing that is approximating. Right. And if you stare at it for long enough, you can realize this also means that this set is a Scott domain. So it's a kind of domain. Not yet. CX is the web. Yes. So I'm going to give another definition. So this was the original definition, I think. Another definition is, right, so a sub-definition. Given any member of CX, is that what I want to say? Yes. We can define member alpha. We can define alpha perp, the negation of alpha, as the set of elements hang on. Nope. Given a subset A of Cx, we can define A perp to be the set of sets beta such that for all alpha in A, the intersection of these has cardinality less than or equal to 1. Okay. Right. So what does that mean? So if I've got a set of sets, and maybe right now this is time to bring in the intuition. So these tokens are meant to be atomic observations you can make of a process or an object. So there might be something like this process can emit the number 5, or the thing I'm looking at has 2 legs or 4 legs or a tail or something. This set of subsets are meant to be sets of consistent observations. And if this thing says, well, if I've got a consistent observation and I forget some, then that's okay. That's still a consistent observation. And if I have a collection of consistent observations which are pairwise consistent, then I can take the union of those and make the thing which is being approximated. Here, what this is saying is if I have a set of observations, I can find the set of all other observations which kind of are happy with that. They overlap for most ones. And then a coherent space is a set Cx such that for all A in Cx, A double perp is equal to itself. So this is, I think this is like a really mind-bending thing, because once you unwind this, it's quite a high power logical statement. It's for all subsets, such that for all subsets. But the way of thinking about it is that this means if I have an observation, its negation is all the things that work well with it. That is to say that it comes out to a unique answer. So there's a unique overlap, or nothing. work well. Yeah. So somehow that a process in its negation should either fail or give one answer. So remember, this was originally designed as a model of functional computing. So it gives you either it fails, as it doesn't terminate, or it gives you exactly one answer. That's the kind of reason. And I should say you can tweak this definition by playing with this. So you can say equals one, and you get a funny thing called totality spaces, and you can say is finite, and you get a thing called finiteness spaces. And this is a very general construction of like this kind of orthogonality. So you do this double negation. So this is a good thing is a thing which plays well with all the things that play well with it. Right? But I'm not going to use either of these definitions. I'm going to use this much more elementary one, which is there is a binary relation on the tokens, which is, so this is meant to be a equals and that is reflexive and symmetric. Okay. So another way of saying this is that a coherent space is an undirected graph. And the way this works is that I said something about coherent observations. So we might have that the observation that something has two legs is coherent without having a tail, but it's not coherent with having four legs. So we can have this different thing. And this is what this relation captures. And if you take the sets of things which are all coherent, rather they all cohere, so they're all related by this relation, so the cliques of this graph, then that suffices to be the set Cx here. So the set of cliques works for all of these. So nice. So I'm going to use this definition. So you can always think what this means is that we have a set of atomic observations, and this relation tells you whether or not two of them could come from the same process. And it's quite some work to show that these three are equivalent. If you know about event structures, which I think one person in the room, then these are like event structures where we have a binary conflict relation. So that's going to be the inverse of this, but no enabling. The enabling is trivial. So you can think of these things as events as well, and this is two events that you might see together. Right. So coherent spaces have a notion of morphism, but it's going to take me a while to get there. Yeah. Mhm.
You're saying that if you just have the event, if you deleted two,
Yeah.
then that would be enough.
You can delete one and two. These are all equivalent. No. These are, this is all one of these. So, no. I'd say that going from here to here is the easiest one. So, here you take the set makes 2x be the set of alpha such that for all x, y in alpha, x is coherent with y. Right, so this is downward closed. And you can check this holds. Going the other way, you can define the coherence relation to be, oh no, hang on, I think there's another one here, which is you have to have singletons. So, all x. So the other way, you can say coherent X and Y are coherent if the set X comma Y exists in there. Going to this one is the tricky one because this is quite a tricky.
The cliques never intersect with each other.
No, they can if they're coherent, right? So I could have the observation that something has 2 legs and a tail. I could have the observation that something has 2 legs and is furry. They would intersect. Now, so they would have an intersection, which is 2 legs. They might not have a union because it might not be consistent to be furry, have 2 legs and a tail. So that's why this has some force, because you're saying I've got a coherent set of observations. A kangaroo. Yeah, but they're not furry.
Oh, yeah.
Yes, it's not the biology department. Right. So there's a number of constructions we can do on coherent spaces. I'm just going to list them. So if I've got X and X is coherence, I can take a tensor product. So the atomic tokens are going to be the product of the atomic tokens. So the tensor product is meant to be a pair of observations which are consistent. So that means then that x1, y1 coheres with x2, y2 if and only if x1 coheres with x2 and y1 coheres with y2. Okay. So I'll get there. It takes a little bit to get to the morphisms. So this is we just want to define morphisms on. This one's a bit harder. Because what I'm going to do is define tensor product and negation, and then define morphisms from those two. So yeah, as I said, there's a negation. So the negation of this is why we get a model of classical linear logic, because we can actually negate the coherence space. The negation is the same tokens, so we have the same atomic observations, but now this is going to be perp two are coherent if and only if either they were not coherent before or they're equal. And the equal is to make sure we're still reflexive. Okay. I mean, yeah, this is confusing. So here's an example. Well, no, here's a family of examples. So if we're given any set A, we can make a flat coherent space where A is a set of tokens and the coherence is equality. So we have a set, and the only thing, they're all individual processes, if you like, and we can make one observation of them, which is that they are them. Now, if I take the negation of flat A, and you work out what the coherence is, it will be the total relation, because it will be they're not equal or they're equal. So it'll be true, right? Yeah. So the negation, and you can imagine this is the coherent space, which is things which are emitting anus, and the negation is the things which are consume anus. I'm going to get thrown off YouTube. Penis. Quality of being, yeah.
You know, stuff in luck.
This coherent space is things which are one particular A, value of A, And the negation of it is things which can consume any A. So it'll be consistent to see a consumer of A's take in A1 or A5 or A trillion. Right? That's the negation of flat A is going to be the observations, the consistent observations we can make about a process which can consume any A. Okay, and you're going to ask about morphisms. So, I mean, it's like a little bit of Boolean algebra to work out. Right, so I'm also assuming that these are Boolean valued. Because yeah, to get the negation to be involutive, so if you negate, so we've got double negation elimination. So if you do it twice, you get back to exactly the same coherent space you started with. Because all the equals bits cancel out. Okay, and then what's a morphism? So I'm going to say that the morphisms from X to here are the cliques of X tensor Y negated, full negated. Right. Why is that? Well, remember from classical logic that X implies Y is the same thing as not X or Y. And remember that or by De Morgan dual is not X and not Y. Sorry, not X and Y. So then this is, if you read this as and this is not, this is giving you the same kind of classical reading of implication as before. But we can spell out what it means. So let me delete these bits. Can actually spell out what it means. So a morphism X to Y is a relation. So a clique, remember, is going to be a subset of the tokens, set of subsets of the tokens. So a particular value is going to be a subset of the tokens. The tokens in this are going to be pairs, so it's going to be a relation R in X, Y, such that, and this is the coherence, if we have X1, Y1 in R, and we have X2, Y2 in R, then if X1 is coherent with X2, then Y1 is coherent with Y2, and this is still under the same thing. If the outputs are equal, then the inputs must have been equal. So this is what happens if you sit there for ages with a big blank sheet of paper and work out what the coherence relation is. The way to think of it is that this relation tells me if I want to see a Y observation on the output, I must have seen a Y observation on the input. So if the two inputs come from the same coherent things, then they must be coherent outputs. But we could have coherent outputs without them necessarily being coherent inputs. And but if we get this relation has to be sort of functional in the sense that if the outputs are the same, the inputs are the same. Sort of. Yeah.
No.
Oh. Oh. X2. Okay. Kind of, yeah.
Sorry.
I'll look at you, yes.
Oh, sorry. Yeah. Maybe it's a little later on this minute. I'm not quite sure I understand what these coherent spaces are actually like denoting. Like for a container, we all know what containers are. There's two and so on and so forth. But I wouldn't know what examples of a coherent space
Well, one way of thinking about them is by starting with there's the coherent space you get by flat. So then if you look at the cliques of this, there'll be the empty set, and then there'll be singleton sets for every element. So you can think of this as either, think of this as the output of a process. Either it doesn't terminate, so we observe nothing, or it outputs one value, so we get one of these. And then building up these other operations, these give you ways of talking about pairs in the function space. So this will be the set of observations we can make of a function that are consistent. So if you sit down and work out, like if I've got, in particular, if you work out what A to A is for some flat A, for some set, then in fact, let's do this for B. In fact, it will be the set of partial functions from A to B is the ones which are represented by these cliques, because this gives you this kind of determinism thing. But
Flat A.
not necessarily.
So
So it could be in a programming language, you'd be interpreting the base types. Yeah.
okay. So it's a pin-based type.
Yeah.
It's typically
So typically in linear logic as a logic, the atoms would be an arbitrary coherent space in this setting. Right.
doesn't follow that term.
No, no. So this gives you very specific coherent spaces where the maximal cliques are all of size 1.
Right, okay. That's why you're saying data types.
Yeah. But if you wanted to, for instance, have a coherent space that represented the Booleans, then flat bool would be the one where it's got 3 elements. We observe nothing, we observe true, or we observe false.
And you could construct that. The other one.
Not the ones on the board, but yeah.
There's not enough.
Yeah. Right, but it is an important fact about again. The it's a way to interpret call by name computation. So this is yeah. There are kind of domains where we always have a bottom, which is the empty clique, and we're always closed under directed joins, which was a consequence of the thing I rubbed off about the thing. So morphisms flat A to flat B are one-to-one with partial functions A to B. Right, and why partial? Because we've got this empty clique. So in particular, the empty relation here is always satisfies this property. That's the function that does nothing. Right, so what's this got to do with containers? Get there in the end. I'll give you one more before I get onto that. So this will do what Ross says. You can get a plus on coherent spaces. So what does this do? This takes the plus of the tokens. So the tokens come from either one or the other. But remember now we're talking about cliques. So we could, in principle, have a clique, an observation, which mixed up 2 halves of this. So the coherence relation says that only in left x1, so this is true if x1 and we have, what should be in left? And in right y1 is coherent with in right y2, but we don't have cross coherence between in left and in right. So it's not coherent. If we're observing a process which promises to either give us x's or y's, it's not coherent for it to give us both an x and a y. Now, what happens if, so an interesting thing is we have negation. What happens if we apply it to these two things? Well, this one, we get another operation which Girard calls par. And this one, you get the product of two coherent spaces, where you are allowed to have cross talk because you observe a product, and sometimes it'll emit stuff from the left side, sometimes the right side, but it's coherent to see it doing both. If we observe it multiple times, it's coherent to see it doing both. Now, the interesting part. As before, we had a sequencing connective on containers that said, if I give you this question, then you get this question. We have another one here. Sure, right. Okay. So the sequencing, we still have pairs of tokens. So we're going to observe two things, but the coherence relation is that x1, y1 is coherent with x2, y2 if and only if x1 is coherent with x2 and if x1 is equal to x2, then y1 is coherent with y2. Okay, so we have an observation. We see, we talk about sequencing, we see x and y, but maybe we also see x1 and y1. We also see x2 and y2. Now, either it might be the case that, okay, just the first two are coherent, but we don't know what the second one are. So that we haven't kind of determinized the first part. But if the first two parts are equal, then the second two parts must be coherent as well. This is going to give us coherence. And again, this is a non-commutative monoidal operator on coherence spaces, similar to the other one on containers. Right. We can also generalize this. So let's say I had a coherent space X, and for every X in the tokens, so everything that could have happened in there, I have another coherent space. So it's not just that I do X and then Y, it's that I do X, and then given what happened, the observation I made, that determines the kinds of observations I can make next. So this is going to be Y. This is a family of coherent spaces. What's this? This is going to be pairs of tokens and the coherence is the same, and it's okay to do this comparison across things because x1 equals x2, so they're going to be in the same family, same member of the same.
You get anything interesting when you like curve of like the sequentialization?
Yes, nothing happens. These two operators are self-dual. So that's to say x, y, right, and this makes sense, right? Because if you think about it in terms of communication, this is, oh no, this one's clearer. This one says, I'm going to admit either an x or a y. So to be compatible with that, you need to accept both an x and a y. If I say I'm going to do x first and then y, then you're going to have to do the opposite of x first and then the opposite of y first. So the fact there's a sequencing doesn't change. So the dual in this is x perp sequence to y perp. So it's self-dual in that sense, like the dualization just goes through.
And is what you're saying about the second triangle
Oh, this one's dependent. So this one, the y is fixed no matter what happens in x. The next part of the protocol is always the same. Sorry, I'm talking about protocols now. But you can sort of say this happens first, then this happens. This one, something happens, and then depending on what happens, so the particular observation that was made in that first thing, if you like the traffic, which is what I kind of call it, then we can change what happens in the second component. So we might say, for instance, this if this was flat natural numbers, I might send a natural number, and then this might be I send an array of that size. This is kind of dependent session types. I think about. Okay. Now to get finally to where I want to get to, we can put these components together and make a functor that goes from containers into coherent spaces. So let's call that, yeah. So it's going to map FSP. And what's this going to be? It's going to be flat S followed by, and this is the dependent one, so it's going to be S in here, followed by flat P of S negated. So if you like, what's a container? It's a kind of description of a protocol where we have to do an S, we have to do the shape, and then you'll get given back a position. And now I went off the definition of the extension. And this is very nearly a faithful functor. So I claim you can also take a container morphism and map it into this, because we go forward on the shapes and then backward on the positions, because this negation also swaps the order of morphisms. And it's nearly faithful if P is always inhabited. And the reason for that is that if P is not inhabited, then these are just the empty set. And the empty set in coherent spaces is sort of viral. It makes the whole thing empty. So you can't talk about just the first part happening. So another way of putting that is if you describe a protocol in coherent spaces using this before operator, there's no way of talking about partial traces. Either you get the whole trace or nothing. Yes, this is faithful if PS is inhabited for S. Maybe I have seen ones where modeling call by value is difficult in coherent spaces because there's inherently always this empty fleek representing a bottom. If you try and do call by value, you want values to be represented by domains which don't have a bottom, because they're definitely going to be there. But you want computations to be represented by domains which may have a bottom or do have a bottom. So coherent spaces, just intrinsic to all of those definitions, Stanmore closure, the thermal negation thing, or the the coherence relation, there's always this empty set representing a computation which didn't terminate. And so the problem is they're kind of inherently they're functional and also called by name. So people have tried saying, okay, maybe what there has to be, there's a special token, which means defineness, and then you can tweak this definition of morphism to say that's always preserved. But I don't think that'll work in this case because oh yes, it preserves sums and tensor up to isomorphism. No, sorry.
Surely, to me, it's just sitting there. It's like just like there are two things that are separate from each other. They can't interact in any way. They're this way. Well, they do that.
I think it's eventual. So I mean, so if you work out what the morphisms are, they kind of end up like this, right? You have seq SP negated as negated RQ, and then if you work out what that is, that's going to be SP. And then yeah, we're going to sort of use sequencing to shuffle the zero. Yeah. But it's forcing you to completely resolve this one before you're allowed to talk about this one. So it's doing that. Because if you use a tensor, you can answer these in parallel, as it were.
Could you sort of shoot not along the next example because you're not separating
Yeah, yeah.
the first part from the second.
Yeah, so the information flow goes, so we come in here, go here, go there, and go back to P. And it sort of forces that on you.
But then you're not preventing other information.
Yeah. Um, okay, so there's more notes. It preserves, sorry, I said, it preserves sums and tensors of containers laxly. So you get two containers, sorry, FC tensor on containers goes to that, and you get sum, but not any of the other. Yeah, it works for sums and products. And if you change the definition of container morphism to allow partiality, it's a little bit subtle, then this is full and faithful. But you also have to know that not only is P inhabited, but also that the backwards path is defined on that inhabited, the witness of the inhabitation to get the thing to work out. So it's not quite as neat as it could be, but I think it's quite cool that you can this idea of a protocol which is in containers can be expressed this way as an operation on coherent spaces. But, oh, container. I mean, so this idea that there are questions and answers. So a very simple question answer protocol. Here's my question. To be a valid answer to that, you have to be in this set. Yeah, yeah, yeah. Yeah, so that's what the sequencing does. I need to know the question before I can give the answer. And the negation tells you the answer is kind of a going opposite polarity. So in particular, this won't be faithful. So at least what I've presented so far, containers are a subcategory of just sets and relations. So you can think of relations as a very general model of computation where an input is allowed to give 0 or many outputs. Coherent spaces cut that down. But if you try and do this with just relations, it doesn't work because sequencing, tensor, and functions are all the same thing. If we just talk about relations, because there's none of the coherence information. Yes, this is not full because these are allowed to be partial. So you could have something where it just be empty, just where it says bottom. Okay, there was more material in there than I thought when I wrote in my notes. But that's it. I have an AGDA file you can look at if you want. Which one? Oh, yeah. Maybe. Yeah, somehow this is just the sum over all the values there. Yeah. Oh, yeah, okay.
So this is the path. So at some point now, here somehow communicate the system.
A bit.
Yeah. And of course, this logic can do communicate.
Which logic?
The logic which you get out of
Oh, yeah.
So is there a way to connect those two models? Is there any insight or to push through verification logic? Coherence becoming fact.
Yeah. Don't know. So yeah. So one thing that doesn't work is well, so it preserves these two, but doesn't preserve sequencing because you end up, if you like, in the wrong order in here. You want to you'll end up with sequence in here and a sequence in here, and you want to kind of do a middle interchange to swap the ones in the middle, and that doesn't work. So that's one problem. Is like the once you can say parallel composition and choice on containers, but once you do sequencing on containers, then that's not preserved, I think, by at least it wasn't, didn't look like it was preserved when I wrote out the definition. Because you end up, so you imagine you've got uh, F applied to C1, C2, and F applied to C1, C2, and you want to sequence them, then you get the wrong sequence. And you get the first one gets sequenced, then you do the second two, and what you want is to swap the middle parts. The sequencing doesn't allow you to do that because it's not used. So it's maybe just a very narrow tunnel that you can't do the interesting part, which is the sequencing. Sure. Yeah. Um, oh, the reason I thought this was maybe interesting is because there are variations on coherent spaces, like probabilistic coherent spaces, where what they do is that instead of you having sets of observations, you have functions from observations into positive real numbers. And then this double negation thing takes, if you have two sets of observations and you take the sum over the ones which are in the fraction, then it comes to less than one. So you get a subprobability distribution on the interactions. And it says you can work all this out, and you get a single probabilistic coherent spaces. And again, it has a sequencing connector. So then you can ask, well, what does it mean to do the same thing again, but then we can have probabilistic um, container morphisms. So this was to try and capture what Jules and the people were trying to do with dependent optics, where they had an idea of what a probabilistic lens was, but not a probabilistic container morphism that worked. I should also mention there's a paper by Glyn Winskell called some things is no, there's much more recent one about where he shows how you can embed. I think it's like functional. Sorry. Yes. He shows how you can embed things like containers and so on into games models constructed from event structures. And it's a very similar kind of idea, but much more complex. But he does actually get full and faithful without this inhibited because you can properly do strategies then. You can probably do strategies that are partial, where they give up halfway. So what I mean by that is that I've got the sequencing, but I can't have one where the X bit worked and the Y bit failed, as in the empty set, because that would make the whole thing fail. Okay. Oh yeah, yeah, yes, yeah. So actually, Glyn's one, these were domains, some DI domains. Yeah, containers is like super simple in some sense. As in, there's no structure on the sets or these. Um, so there's a more general setting where you have an indexed category. And so this was set, and this was families of sets indexed by that set. You know. But you can also define a kind of category as the Grothendieck construction, where you take pairs of a shape, which is an object of C, and positions are an object which is in L of there. And then so you can reconstruct containers from this and also loads of other things. This is like, so that's a kind of massive generalization to the point where most of those constructions I showed you before don't work automatically. You have to assume more and more things about C and they'll work. Yeah, it's a categorical. That's one. So some people call these F lenses because they use F instead of L, or generalized lenses. And there's also cases where people add more structure to this. So this is like Donnell, Almond, and Talma Oosthuizen's update lenses. So you can think of this. Another interesting one is S is states, P is changes or tangents. So you can think this is my set of states, and this is the set of like changes I can make to that state. And then you might have another operation that says, given a state and a change, I can get a new state. This allows you to describe transition systems within these things. Or, or you could say it's possible to add tangents, things like that, so you can get a kind of formal differentiability. Yeah. Yeah. Yeah, yeah. Well, I think it's states and no, hang on, it's position. Yeah, positions where you are, position as in state in a spatial sense, and S is no P. Yeah, P. No, the problem is the other way around. So it's P is positions and S is steps. I think. But I mean, you might expect like just from this basic, this definition says almost nothing. Says I've got a collection of things, and for everything I have another collection of things. So there's a lot of things that fits into. And
Trying to find mechanisms where the things are swapped around.
yeah, problems and solutions, shapes and positions. Yeah. Yes. So you can do P. And the intuition there is that P is all of the S's, all the things. Is this? You can go from here to here by P is equal to this sum sigma S PS, and it projects out the first one. Yeah. But that's a kind of category theoretic way. Is that literally this is just a pair of sets where for each position you tell it what shape it came from, rather than for each shape you say what set of positions you're in. Yes. Okay. We're done. So no questions online? Oh no, we don't do it.